Afternoon, and welcome to our session on ontologies and linked data. My name is Jörg Surefetter. I'm your chair for the session. I'm not Marie Esther, as you can tell by immediate sight, but it's a pleasure to stand in for her. I welcome you to this session. I would like to make you aware of the fact that this is video recorded and also live streamed. So if you're participating, especially in the question round afterwards, your question and the answer will be live streamed and recorded. If you do not agree with this, I would kindly ask you maybe to leave the room by now. Otherwise, you're of course welcome to join the session. We start with a paper presented by Irene. It's a framework to build games with a purpose for linked data refinement. Irene, the floor is yours.
Thanks a lot, Jörg. So this is a joint work with my colleagues, Georgia, Gloria, and Andrea, in the context of a European project named Stars for All. So we had the wonderful panel yesterday about knowledge graphs, and we are keeping talking about large-scale linked data and management. And linked data refinement is an open topic, which is very well researched in this community, and usually the techniques to do linked data refinement are based on machine learning or statistical learning. And when it's come to that, you need to train a machine, and to train it, you need to give them some true data, some training set. And to get that training set, you need to ask somebody to put it together. So in the end, in order to train the machine, you still need humans, either expert or generic audience, to put it together a training set. And this means in the linked data refinement case that you need people to solve tasks of linked data refinement so to get the information required to train a system. So there are several strategies to collect data from users. That come from crowdsourcing, human computation fields. And in the semantic web community, they have been employed a lot for collecting triples, verifying triples, making ontology alignments, and every kind of stuff. So these methods involve a user to solve some task, and in exchange, or to motivate them to do that, they use different kinds of incentives, from paying them, like in traditional micro-working platforms like Mechanical Turk, for example, to giving premium access to resources, to train them, so giving them knowledge or giving them recognition for their work, and giving also fun incentives. So today I will talk about the last one. So we are talking about games with a purpose, which are a kind of gaming application in which people play as players. So they play in order to have fun, but as a collateral effect, they are solving some task. So the resource, since this paper is from the resources track, the resource that I'm presenting you today is a software framework that we name WAP Enabler, that allows you to build games with a purpose for linked data refinement, so that the players of the game solve your linked data refinement tasks. So the pipeline is that people play games in order to have fun. As a collateral effect, they are executing tasks, and those tasks can be used as training set for a machine learning algorithm. So why the need for such a software framework? Because we think that there are a family of linked data refinement tasks that are quite common, and there are some game mechanics that can be reused as well. There are also aggregation algorithms to collect information from multiple users and making sense of them. And last but not least, to save effort. So developing an application from scratch is expensive, so using a framework that is already there and thought to do that can be very, very useful. So which kind of linked data refinement task are we talking to? I'm talking about data linking, meaning drawing links between resources. Well, I think I don't have to explain to this audience what links means. The three cases that our framework supports are first, creation of links. So you have two resources and a predicate, and you draw a link between the resources. And what you can do when you create it or afterwards is that you can assign a score that is your confidence in the truth value of that link. So the games will be used to create or update that kind of score on links. So the second case of data linking is link ranking. So you have two links. To each link you assign a score, and you can make an ordering of scores. So to put those links in an order of recognizability or popularity or stuff like that. The third case is link validation. So if you think that some links are true and some other are false, you can set a threshold, and when the score of the link overcomes the threshold, the link can be considered true, and all those links that have a score lower than the threshold are considered false. So that's the basic things that are supported. So I will go very briefly through what is inside the framework. There are more details in the paper, and you, of course, can ask me more afterwards. So first of all, the game mechanics. So as I said, this framework is designed to support the specific game mechanics that are very popular and can be reused. So each game gives one task at a time, and each action of the user is solving one task. The games are usually double player games, so it means that each player is coupled with somebody else, and they have to come to an agreement on what they think in order to get points in the game. This is an incentive for the players to play fair and to give the right answer, let's say. Third thing, output agreement. So the agreement between players is on their answer. So there are different kind of game mechanics, and this is based on output agreement. Last but not least, we are also injecting gold standard tasks, so that are tasks of which we know the right solution, in order to check the reliability of players, so that we avoid players just playing randomly. With respect to the aggregation, so the truth inference algorithm, each player contribution is considered a single evidence on the truth value of a link. Those contributions are weighted with the reliability I was talking about before, and we have implemented an incremental truth inference algorithm, which means that as soon as the score, for example, overcomes the threshold, you don't you don't propose the same task to any other player because the task is already solved. This minimizes the number of players that are required to solve a task, and also define those tasks that are more difficult. If the score does not increase over time, it means that the task is either too difficult or simply it's too confusing and it's not to be solved anyway in the game. So it's a software framework. So how it is built. So it's a very simple web application. There is a database. There are, of course, also all the structures for points, leaderboards, badges, and everything that are related to a game. I wanted to point out those three tables that are the subject table, the object table, and the table that, of course, express the links with their score. And the only, let's say, requirement that we put on the data that must be fed in the game is that each resource must have a sort of visualization. So if it's a text, a document, the text can be the visualization. If it's a picture, the picture is by itself. If it's, for example, a point of interest, maybe their coordinates are the way to visualize the object on a map. We also set up a number of predefined API, both for loading new tasks in the system and for getting out the solution, the aggregated solution, and the triples directly out. We also set up a predefined client application for the game. We built it on traditional HTML5, AngularJS, and so on technologies. And we designed also with a mobile-first design, so they are responsive and they can be easily used also from phones. And last but not least, we are releasing all this framework under an Apache 2 license. So I'll go through a number of applications that we built in the last few years on top of this framework and while building this framework, actually. So the first one is named Indomilando. The purpose is link ranking. So in this case, we are talking about cultural heritage assets in Lombardy region, in Milano in this case. And the game proposes you the name of an asset and 4 different pictures from 4 different assets. And you have to guess which one is the right one. So once you click on one of the pictures, you discover if you get it right or get it wrong. So in this case, we have all the links, the correct and the wrong links. The links in this case is the asset is linked to the picture. And by asking people, we are trying to get which links are more recognizable. This is because the pictures come from a repository that was built for maintenance reason of those cultural heritage assets, not for example, for advertising or for tourism. And so we were asked to build a game in order to identify which are the most recognizable assets and which are the pictures that best depict those assets. So it's a pure game with a purpose. There are points, badges, leaderboards, as in any game. The game also showed an interesting educational collateral effect because people were learning to recognize assets. And the link ranking is a result of the agreement. So the more the people recognize it correctly, the more that score was let's say, reliably recognized. The second one is the land cover validation game. This was designed in order to validate links coming from 2 different, actually, machine learning algorithms. So it is those 2 algorithms. One was from the local institution and the regional institution, and one from an international institution. It was intended to assign a land cover classification on the ground. So you have this aerial picture with this small box, and you have to classify what land cover class applies to that box. So we made this game played during a conference, the FOSS4G conference. It is a free open source software for geospatial application. So the player was scoring if he got one of the 2 classification, and the goal was to discover which of the 2 classification was more accurate. The last example I want to show you is a Night, and it's a game to classify images taken on board of the International Space Station. Those images are classified and then used in a pipeline for measuring the light pollution effect in cities. So those photos are partially from cities from above, partially of Aurora Borealis, partially of astronauts themselves, and so on. So people in the game had to guess which of the class was correct. And it was also a bonus because you could then download the higher resolution picture from the NASA website. And again, the player get points if he agrees with somebody else, and we increase scores until we know which is the right classification. So if you want to use it, you can download it, and you can also follow a tutorial. So we set up a full end-to-end tutorial to understand how the framework works internally and what needs to be modified in order to fulfill your own purpose. And this actually happened. So I'm happy that Matteo is in the room, because people from the University of Milano Bicocca actually took this framework and built their own game. They are dealing with analogical reasoning, so they were trying to get example of analogies. In this case, is David Letterman is for the United States of America, as Mr. X is for Italy, and then you have 5 popular TV people in Italy, and you have to find which one. And the nice thing I want to report is that they did it on their own. I mean, we didn't almost make any effort in explaining them how to use the framework. So I think that I can say that the framework is easy to use. So to conclude, the framework is an open source framework to build games with a purpose. It implements frequent cases of data linking. It can be used to collect training sets for your machine learning algorithms. And it is thought to save you time and effort and to let you focus on your actual goal, research goal. And the next steps is to add additional cases, data linking cases or linked data refinement cases, apply to different domains, and of course address all your requests, requirements, suggestions. So thank you.
Thank you very much. Thanks, Irene, for this nice talk. It's time for questions, and we're over. Paul, I give you the microphone.
Very nice. 2 quick questions. One, do you have any kind of measures of how long it would take you to build with one of these games?
That's a good question. I think you mean using the framework as it is, or when we didn't have the framework?
When you're using the framework as it is.
Then maybe Matteo can answer. I think that a few days. If you have a clear idea of what your purpose is, and you have the data already there, let's say, the task already there, I think it's a matter. Yeah. Yeah.
Further question? Anyone else? Maybe we switch in between. You can set up already, yes, please.
Okay, so mine is really quick. Do you work only at the granularity level of 1 triple at a time, or can you extend it to consider several triples or RDF snippets for evaluation?
Currently, the framework supports 1 triple at a time, but I think it can be easily extended to have a subgraph or whatever. The important thing is to feed the system in order that each of the, let's say, resources in terms of the system can be visualized. So if you can visualize 1 subgraph, that could be the subject, let's say, of the game very easily. So Paul again?
Yeah, sorry. No, there's... Anyway, quick, did you do a lot of software documentation?
We did, actually. So if you go to the GitHub website, you have both the framework by itself and the tutorial that documents step by step how to modify it and where to put your hands in order to get your game up and running.
Yeah.
Hi.
Hello. This is really nice work.
Thank you.
My question is about how easy it is to extend or to modify the game mechanics that are already in the framework.
Well, I started developing games with a purpose in 2008, I think, and we tried several different mechanics. But in the end, I think that this is the easiest and the most common one that you can think of. If you want to apply different game mechanics, of course, there's some coding to do. I cannot estimate how much it takes because it really depends on how much you want to modify it. Okay. I think that this mechanics covers 90% of the cases, at least in my own direct experience.
Okay. Thank you.
Oh, there's even 2 further questions. Maybe make it quick. We are almost done with our time.
So maybe a quick answer to, I like the resource, but I was wondering what kind of related work existed. So why is the need for this framework? I think you said a bit about it, but is the related work not sufficient already that can be used? And I don't know. I don't have an overview. Just a very quick comment maybe.
So when you want to collect data from users, you have different options. So of course you can go and use a crowdsourcing platform, and that's of course already there. If you want to develop a game, as far as I know, this is the only framework available. Otherwise you have to code it yourself from scratch. And this is the reason why we did it. Actually, since we developed a number of games over time, we did it the framework for ourselves first, and then for the community.
Very interesting work. Thank you. I'm wondering if there's any correlation between the funness of the game interface, right, and the quality of the tasks achieved, right? Because intuitively, if the interface is really fun, a lot of animation, maybe some shootings involved, right? People may be more engaged, right, and to do a better job at achieving the task.
So thanks for the question. So as I said, we experimented different things over time, and it depends if you want to maximize the number of users and the time they spend playing, or if you want to maximize the data that you collect. So in this case, it's not meant to be a game that is addictive that you play over months. Even if, in the case of Indo Milanto, we had one person that managed to play with all pictures in the game because he really liked the game. This is a very simple mechanic, and so it's a sort of casual game. Of course, you can make it more interesting or more sexy from a user experience point of view, but you must make sure that this does not negatively impact the actual purpose, that is collecting data. And
maybe
it,
you
of
can
course,
chat a bit afterwards, even though.
Yes, sorry.
Thank you very much.
Thank
Elena.
you.
Thank you. I have one quick question. Is the person who's presenting the LOD Atlas present? Okay. Could you come in front of me? I'll just to have a quick check in between. I'd like to announce the next speaker, though. Welcome to the audience who came in intermediately. Please be aware we are recording this and we are live streaming this. Please welcome Gesim, and with his talk, LoadStats, Distributed Computation of RDF Dataset Statistics. The floor is yours.
Thank you. Good afternoon, everyone. My name is Gesim Sedi. I'm a PhD student at University of Bonn, and today I will be talking about distributed LoadStats, distributed computation over RDF dataset statistics. Basically, during my talk, the outline of the talk is like following. I will give an introduction and motivation why this is important for the community, and also I will go through the approach we have chosen, a bit of empirical evaluation we did for the resource, and also the use cases which we are aware that they are using distributed LoadStats already. And I will conclude the talk and give some hints for the future work. Over the last 2 decades, a semantic web community has grown from the mere idea of basically designing the modeling of the data to the more broad array or based on the protocol and standards, which could be for the publication exchange on the web. And this basically give us that for the record today we count more than 10,000 data sets available out there using these semantic web standards. Plus many others which basically are kept private for so many reasons. Thanks to these standards, the data are becoming, large data sets are becoming machine readable, and but nevertheless these data may not fully benefit from the data without having an a priori statistical information from the internals of the data and the structure of the data. For that reason, we may need statistics, right? And statistics are basically useful for such cases like vocabulary reuse, when we want to find the vocabularies which are suitable for your data sets, coverage analysis, which those data sets contains the necessary information and you need, privacy analysis, does your data sets contains any sensitive data, and also like link prediction, which data sets are basically suitable for doing the interlinking or link prediction on your case. So, as I mentioned, we need statistics. And for that reason, there have been many tools out there who do those statistics based on the instances or even in the schema level. But they basically were they were struggling on the data when the data becomes too huge or even it's larger. For that reason, we need something which basically is capable to scale out to the larger number of the cluster. And for that, we propose a distributed LoadStats, which is a software framework which computes 32 predefined statistics over large scale using Apache Spark and Apache Flink as well. But before I go to the internals of the distributed LoadStats, let me introduce our beautiful project, which is called Sansa. Its core is basically a distributed data flow engine which does reading, inferencing, querying, and machine learning over these large RDF data sets. And it is basically a modular framework which contains different layers like knowledge representation and distribution, inferencing, querying, and on top of it we have some analytics. And the distributed LoadStats is basically part of this larger framework which we have built on it. We adopted this statistical criteria from the paper which was published from Demter et al. In 2012. And then those statistics we have just, in contrast to them, we basically have used our large distributed computing framework like Apache Spark in our case. And the statistical criteria basically is defined as the triple of FDP, where F stands for the condition operator like Sparkle, and D is the derived data sets from that filter which we operate on top of it, and the P is basically the post-processing operator, which could be optional in case you don't want to use it. And we basically use RDDs basically we do use RDDs of triples as an internal structure for applying those statistics on top of Apache Spark. First, we have to load the data on the large-scale storage, which Spark can read efficiently. In our case, we use a Hadoop distributed file system. And afterwards, we use Sansa functionality to basically read fast and apply a different strategy of querying the data. And for that reason, we have this RDD of triple, which we call main dataset. And afterwards, we apply those rule, filter, and post-processing defined from each of the statistical criteria. And in context of Spark execution, basically it generates an execution plan which it's optimal for executing those statistics over these large-scale data sets. And in the end, we, of course, produce and void description of the statistics for better machine-readable data. Just to have to give you on a brief how the workflow of the distributed LoadStats works. Basically, the data should be loaded on HDFS. I mentioned it, and then we use Sansa Engine as a distributed framework for computing those statistics, which could be from those 32 we have collected, let's say just 5 here, but we will get an example for class distribution, which covers the usage of the class to the whole data sets and give the frequency of the classes to the given data sets, which is defined by this rule. Let's say a filter, which basically mentioned that the property should be type and the object should be URI. And then those are basically using, on Sansa you can just read like easily with one line and perform those statistics and get those statistics on the fly using Hadoop ecosystem, right? And in the end, basically the second is this filtering I mentioned, and then we apply this action, which basically just aggregate or takes the counts for this class distribution over different nodes. Depends on your cluster configuration, right? And after the class, this cluster configuration set reduce has been performed to the different nodes. Then we collect the data in the end to the master, which basically gets you the sum of each of the classes which has been used on the data set. And of course, this could be visualized on using WebWall or other web ontology visualization tools. And also we have Sansa notebooks, which basically can also you can also run your code snippets on the web editor. The aim of our evaluation was basically to see how well our approach performs against non-distributed tools, and also to see to do a bit of analysis how well our approach scales out to a bigger number of nodes on the cluster. We basically try to address those three questions. How does the runtime of the algorithm change when the nodes in the cluster are added? And how does the algorithm scale to the larger data sets? And the third one, how does the algorithm scale to the larger number of the data sets which we have played around on the evaluation section? We have basically carry on two sets of experiments. The first one is mostly on checking out how well our approach basically performs on a distributed manner, and the setup of the cluster is as follows. We have run this on the cluster with 6 nodes, 1 node as a master and the 5 node as a worker, and we have carried out the data on the same HDFS cluster as well, and I guess the Hadoop was 2.8.0 and the Spark 2.2.0 and the Scala 2.11. And the data sets, we have chosen 2 real-world data sets and 1 synthetic data set just to see out how the size-up scalability works in our approach. In this case, we have basically set up 2 experiments. One checking out if the distributed LoadStats performs well also on the local mode and also on the cluster mode against the original LoadStats. And we basically have seen that on most of the cases, distributed LoadStats basically finish the computation, and the LoadStats basically fail on most of the cases. In only one case, and also outperform distributed LoadStats, and the reason is because the LoadStats runs on each file separately, and for that reason, the runtime basically was collected to each file, which are pretty small. In our case, distributed LoadStats basically compute as a full graph. And then we also have run this on the cluster when we kept the number of nodes 5, and we have seen that the geometry mean is like more than 7.4 times faster when we run on the cluster, even though the cluster is small, a commodity cluster. Yeah, the ratio has been computed basically the runtime divided by the runtime on the cluster divided by the runtime on the local mode minus 1. This also implied that distributed LoadStats shows consistent improvement for each data set when the number of workers or the cluster has been bigger. We also wanted to measure the node scalability and size-up scalability. In order to measure the node scalability, we kept the dataset constants, like 15 GB BSPM datasets, and we basically vary with the number of we kept the number of workers constant, and we varied with the data set. So basically we increased let's say the number of magnitude 3 the data set. We were able to run until 1 terabyte of data in this cluster. And we have seen that the trend basically is quite near linear, or even sometimes is super linear, because most of the tasks were able to perform using Apache Spark in the fast manner. In other case, we also tested out the node scalability when we kept the size of the node, the size of the dataset constant, and we varied the number of the nodes in the cluster, and we have seen that for sure the scalability or the speed up were pretty super linear, and we are really happy that that happened on our evaluation. And we also computed the effectiveness of distributed LoadStats, which basically measure the efficiency of the resource, and also how effective is on which number of nodes it reached the point when you don't need to increase the number of nodes anymore. And we can see here that, let's say, the trend basically is super linear, or even sometimes near linear, and the efficiency goes until to a number of 4 nodes. That we can also remove one of the nodes. Depends, let's say you want to use a cluster somewhere like Amazon on Databricks, which basically you somehow assume that how many nodes you may need to run your application on the cluster. In order to basically show you the usability of our resource, we are aware for those use cases. One of the use cases which comes because we were inspired to do this work was from the LoadStats, which basically crawled the state of the art or current state of the LOD on the cluster. And the distributed LoadStats, on the LOD, and distributed LoadStats has been used as an underlying engine for those data sets which basically are not able to run from the LoadStats. The second use case is from the Aletheia use case, which basically are an Ethereum data sets, are devised and contains more than 36 billion triples, and the distributed LoadStats was run on the Databricks notebooks over 100 nodes cluster. And the third one is from Big Data Europe project, which is an easy-to-use framework which basically contains the different big data frameworks, and so it contains a lot of logs, and distributed LoadStats has been used to basically generate statistics out of those logs. And the fourth one is for Upstat, which basically has been used for those dataset statistics which Upstat were not able to generate. Yeah, to recap, we basically obtaining the overview of the web of the data. It's considered to be data intensive and also computing intensive. For that reason, it's a challenge to find out a really scalable and efficient framework which shows you the internals of the data. And for that reason, we propose distributed LoadStats, which basically it's a novel software framework, part of the larger Sansa framework for computing those RDF dataset statistics on the cluster. And of course, we are glad and happy for the scalability. We still want to perform further improvement on the scalability and the load balancing for doing more intelligent indexing and also intelligent partition of the Spark. Thank you for your attention, and yeah, I'm happy for your question, to answer your question.
Thank you for your talk. Time for questions. Where do we have a question? Over here?
Hello, thanks for the talk. I want to ask, it seems from the presentation that in order for you to be able to compute the statistics, you actually need to have the data loaded in your storage. Is that right?
Yeah, it's right.
Okay, so this is different, right, from the original LoadStats, which used Spark endpoints that were already on the web to compute the statistics over the data that they did not have, right?
Yeah, it's right. For that reason, we basically have done this because relying on Spark endpoint, it usually doesn't work for larger data sets. So we wanted, I also forgot to mention that we have this Satisfy, which basically is a REST interface for distributed LoadStats that everyone from elsewhere can basically run to the bigger data sets which were not able to crawl from LOD Cloud or LOD Stats. Yeah.
Okay, so maybe a follow-up question is, can we then use your distributed LoadStats framework to compute the real overview of the web of data, like based on the Spark endpoints out there, like LoadStats did?
Yes, there is. Because right now we are working with DBpedia community, and they have introduced the data bus, which basically you can also just generate your own data sets and plug into DBpedia. And the idea is that we will also roll back the data sets to the DBpedia itself, so everyone can basically generate their own data sets to DBpedia, and we trigger those by the Spark endpoint, and we generate the data sets on the fly and give them back to the DBpedia itself. So that's the plan. It's still ongoing work with us, but this wasn't as a use case here because it came after the paper.
Okay, one more quick question. Could I make a quick check? Usually we are not encouraged to switch talks in the session. However, Ricardo has a problem because he has in parallel a Minute Madness and they are quite late. So we would like to offer him to give the presentation first, and then afterwards would be the presentation from Hande. I hope I pronounced you right. Is anyone objecting to that solution? Okay, so we do it like this. Please prepare there, and we make the next question as well.
Yeah.
Hi. So I was wondering, since you have edge base for like storing the graphs, have you thought about like computing statistics on the evolutions of graphs over time, like exploiting one of the columns for like time and see like the updates of the graphs, something like that?
Basically, we haven't used HBase for keeping the data there. We have used only HDFS to keep the data on the raw data. So we haven't thought about that. Right now, there is a work, because Sansa is a big project. Basically, we are plugging in everything there. And one work is on quality checks. We basically want to see the quality checks of the data, or the quality assessment of the data on demand, which you can also see in different time slots what the data was there. But we can also consider that for statistics as well. Good point. Thank you.
Thank you very much to the speaker. Thank you.
Thanks.
Sorry? But it was nice, though, wasn't it?
It just doesn't fit the...
Reconnect?
yeah, but this thing, this table...
Uh-huh. Should I give you a hand in the meantime?
It
while
doesn't
presenting?
work. I didn't expect it. There was a...
Do you need... Has someone a different adapter for Mac?
No, it's rejected. It was working? It was working at some point. All right.
Magic.
This is flat and this is small.
No, don't touch it.
All right.
Thank you very much. Okay, let's welcome the next speaker. Ricardo will present the vocals, vocabulary, and catalog of linked streams. The floor is yours.
Okay, thank you everybody. I say my name is Riccardo Tommasini and I am a PhD student in Politecnico di Milan. I would like to present this work, which is a joint work with a lot of institutions, as you can see. I will not name them. Oh, yeah, the mic, sorry. I will, better? No, this one only? Okay. Okay. I will not name them all because too many. So, okay, so this way. Sorry. All right, so let me first give you the motivation why we're doing this. Data on the web are highly dynamic. This is an infographic we got, which is every year updated. And you can see how in 60 seconds, a lot of information is produced on the web, spanning from posts on Google, from Facebook, messages, WhatsApp, a lot of things. And this trend is growing. Every year, a lot of information is processed, which makes us thinking whether we can treat this information as a stream, as it is in nature, right? You are used to store that and process as batch, but we can perform much more. Unfortunately, when we reach the web scale, we got a lot of new challenges, not just the velocity, but we got also variety and veracity. These data are messy and incomplete and inconsistent, so processing them requires the employment of semantic technologies. So the question we are trying to answer is this one: can we process streams on the web? So let's take the basics, right? Let's think about how is done a stream processing application for those of you who don't know. So we got streams, which are simplified as water, because I think conveys the idea. Then we have queries, right? We have these queries are special, not like usual queries. They are standing queries. They are registered ones. They never change, and data flows to the query. And these queries are posed by different people. Like you have data engineer, you have data scientist, you have analytics engineers, and they might be interested in different perspective on this data. So you have this language here has to be as expressive as the user of the language requires it to be. Okay, both these ingredients, the streams and the query, are fed to an engine which is responsible for executing the query over time. as long as keeping up with the volume and the velocity of the data coming in. So this engine must be very scalable because data are flowing into it. And here we can open like an hour of discussion about what happens if something goes wrong, but that's not the place to do it. So this is a stream processing application, but what is missing to go to the web, right? So let's think about what happened to linked data, because the story is kind of parallel, right? In linked data, so this line divides the web and not web. I should have put clouds, probably. The below the line is not web. So we got databases, or plain databases. I'm not speaking about the data format, but think about relational databases, right? And we have schema languages, which you can use for organizing our data. And then we have SQL, the part of relational algebra that we use for querying. This was the set in the 70s and in the 80s, and actually is a set still today in a lot of institutions. So to put that on the web, we started from, create a language, Sparkle, we create schema languages like OWL and RDFS, and of course, we create the beloved RDF data model, which helps us to do data integration and also produce shareable sources, right? That's very important. We want to spread the word with our information to reach the web. So the question is, right now, can we repeat this story? Well, we tried, but let me give you a bit of recap of what my community, which is the stream reasoning community, did in the last 10 years, basically. We started with, so again, the line says web, not web, and below the line we have no web. We identified the key abstractions of stream processing state of the art as it happened for static data. So we have data streams. In this case, I need to show they were internally, so the icon changed. We got CQL, which is the continuous query language. It's a project at Stanford by Jennifer Widom, which was done during the beginning of 2000, and is the most prominent language, which extends SQL. I'm not going to go in details unless you want to know afterwards. Just think about like a special kind of SQL for streams. In between, we have the plain old schema languages. They don't change, which is an important thing. We kept it. The extension we did for the web was, symmetric to what linked data people did. Sorry for the backwards going, but we did RSPQL, which is actually the last contribution we did in order, which is the extension of Sparkle to either query this data, but also explain the semantics of the operational semantics of the engine that actually do the querying. We got RDF schema and OWL, and here I put a question mark because it's not clear whether we need to extend these two. There are ongoing work here, but at the moment we kept the semantics as it was, like in the down, right? Like for relational schemas. And we did RDF streams, which is the whole point, right? So RDF streams are our way to share streaming data on the web. But is that all? Probably not, right? That's what, otherwise I won't be here. So the idea is that it's missing something, and to find it, we need to go deeper in the linked data work. We need to go back to the linked data principle from Tim Berners-Lee, which was here, I don't know, a few days ago. The first thing is identifying using URIs, for identifying things, and that we do that too, right? We need to use HTTP, and that's one of the first problems, because for streams, HTTP doesn't look like convenient, right? You get in data every millisecond. If I have to do a request every millisecond, that sounds heavy, right? And my server is going to blow up. And also, I might not respect the timeout. Then we want to, is an important principle, which is what all this presentation is about. When someone look up a URI, they references it, you need to provide a useful representation of the resource it is looking for. And that's what we're focusing on. Because if I'm dereferencing a stream, I need to provide you a useful representation of what a stream is. But a stream is an unbounded set of data. How could I represent the infinite? That's not so clear. And finally, the fourth principle is interlinking. And again, linking something that is infinite sounds like tricky to do. But yeah, we'll go to this again. Recapping, for data set, of course, we fulfill all these principles. Although for data streams, we kind of have troubles. Definitely, HTTP is not enough. We need more protocols. And linking is not really clear what to do there. Then I put there a bunch of form of representation. Sorry for the imprecision. It actually comprises a lot of things. And I didn't have time to go too much in detail. But what I want to focus is the shared vocabularies. What distinguishes at the moment streaming linked data from linked data is the presence of shared vocabularies. I mentioned three: dcat, void, and DC terms. These are the tools that people use to create metadata for the data sets. And as Natasha and I showed this morning, these are very important for their retrieval, discovery, access. We don't have something like that for streams. We need it, so we did it. Let me show an example. So let's say I want to annotate the stream of traffic observation in Milan, and I use void. And like best practice asks me to, okay, call it data set. This is just syntax, I know. But I need to define data dumps. I need to define class partitions. How can I partition something which is infinite? I don't know. I mean, all these things are like out of, not domain specific for streaming data. And we require a more precise language. And here it comes, vocals, which is actually the second generation of this language. We merged voice, and which was the vocabulary of interlinked streams, with the web of stream vocabulary, which were done in the same moment. And we decided to merge them into a single resource that the community can agree upon. Just to give an overview of vocals, is an OWL2QL vocabulary. We chose this language to welcome ontology-based access usage. This profile. It allows you to model streaming services, stream transformation, and not only streams. And of course, is available on LOD and GitHub. But let me go deeper. So the streaming, the motivation why we need vocals is that we are trying to solve basically three main problems. The first thing is discovery. Stream must be findable by the means of URIs, of course. And we need, even though HTTP is not enough for provisioning the data, we need to be backwards compatible. Otherwise, we won't, join the linked data word, right? People expect to define something like, this is a stream. And okay, I need to, get the good tools to process it, but I cannot get an empty answer. I need to know what I'm, obtaining. So we need to give description through HTTP. The second problem is access. Negotiation must not be only related to content, but also to the protocol that I'm able to process. If I'm able to get data in a push-paid manner, I need to tell that and to ask for that. If the only way I can get the data is through HTTP, I need to bargain with the server a solution for that so that I can actually get my data, right? So protocol negotiation is a new frontier, which wasn't there in the principles. And we need to distinguish between endpoint and access URLs, because endpoint, when you decouple these two things, it becomes clear that an endpoint is the representation of a stream on the web, while its access URL is how do I actually get data, like the provisioning, which might be whatever, right? WebSocket or MTDQ or Kafka, if you like it. Finally, the provenance is very important because stream-to-stream transformation, as the name conveys, they produce streams out of streams. So basically, you need to understand how a stream is generated and decide whether you still trust or not the source who produces it. I'm going to go fast through just the core model, which is the simplest one. Basically, it extends the cat with simple abstractions. The data set is extended through stream, and we add the concept of finished stream pastition for several reasons. One of them, you want to possibly let the user understand what's a sample of the content of the stream. The second point is that the stream descriptor is the file, which is actually staying on the web. The second module is the streaming service, and it actually is very simple at the moment, and we used the RSP environment as a model, but of course it's extensible. The idea is that we got publishing services, processing services, and catalogs. Catalogs are obvious. Publishing services and processing services are actually defined in terms of their features. I know that might recall for some of you semantic web services, and that's scary for a lot of people, but not that complex. We kept that simple. The thing is that if I am in a web environment and I assume that different endpoints can cooperate either or in a choreography or through an orchestrator, they need to know what they can do, right? They need to share this information. Simple example. We have a triple wave, which is a publisher and shares the data. This is what the feature can do. It can replay a stream. So if you ask me to start again, it gives you the data back, it tells you the format and the stream it can produce. RSP engine is my processing service and also a catalog, because I can ask him both the roles, so I can interact with it in two ways. And he has different features which tell me which is the operational semantics that he has, so that I can track the provenance. I was sorry I didn't go in detail on the provenance, but that's too specific, and I think that the best way is using the extensive documentation. So I want to thank Yeya Abosedira, which is the master student who helped me with this. I didn't name the other authors of the paper, but I really care to name him, because he actually, there are too many other authors, but this guy did an awesome job, so I want to thank him. And now I'm happy to welcome question. Thanks. One more thing, let me advertise this velocity on the web track at ISWC.
Thank you very much. I think we make one quick question, and then you can jump to the Minute Madness, okay? So do we have a question from the audience? Where's one? Over here? All right. I would have some too, but the audience always has priority.
Thank you for switching.
Thanks for the talk.
Thank you.
You mentioned extending DCAT so that you can catalog basically streams.
Yeah.
I just wanted to make sure that you know that there is DCAT revision currently undergoing.
Okay.
So one of the things they did is they added data services and data distribution services. So I think the stream part would go there quite nicely. So
cool.
Just if you could take a look and maybe raise an issue to integrate streams.
I'll spam them for sure. Thank you. Thank you, everybody. Bye.
Thanks again to the speaker. And good luck by the madness. You'll do it, I'm sure. Take a second.
Increase the resolution? That's
okay.
Or decrease it. No. What is the appropriate resolution for this?
Oh, that's a good question. Anyone an idea? You could maybe plug out and plug in again. That helps with many technical systems. Which always worries me. If we all have all these self-driving cars, switch on, switch off to reboot again, I'm not so sure if this is a good solution. All right, here we go.
Okay.
Okay? Oops.
Okay.
All set?
Okay.
Excellent. Welcome to our next and final presentation in this talk. Thanks for agreeing that we do a little switch. I'd like to welcome Hande, I hope I pronounce it correctly, on her talk on browsing linked data catalogs with the LOD Atlas. Please.
Thank you. Hello, my name is Hande Gözükan. I work as a research engineer at INRIA in France. I'm going to present you LOD Atlas, a linked data catalog browser to browse linked data sets developed by research team ILDA at INRIA. This is the last version of LOD Cloud published in August 2018. I guess this image has been one of the most used images to emphasize the growth of web of data. And actually there are thousands of other data sets out there published through data catalogs or Sparkle endpoints or by other means. And as a user interested in linked data sets, I'm quite happy that there exist so many data sets out there. But also, as the number grows big, I have a problem. How can I find the relevant data sets? Many tools with different approaches have been developed to address this problem. Semantic web search engines, open data catalogs, summary tools, datasets and frameworks like LoadStats and LOD Laundromat. They all provide useful information, but taken individually, they provide just partial information about the datasets. And users still need to visit multiple such resources to get enough information about the datasets to identify the datasets of interest. So when we started developing LOD Atlas, our main motivation was to facilitate finding linked datasets for the users. And we have investigated several tools and the data that they provide to achieve a coherent view of datasets. And our main contribution is to present aggregated data from multiple resources on a single platform with search capabilities and interactive visualizations. So what is LOD Atlas? LOD Atlas is a web tool that enables users to find the datasets of interest through keyword search, URI search, faceted navigation on datasets metadata and schema-level contents aggregated from multiple resources. And the platform also allows users to assess the relevancy of the datasets through a series of interactive visualizations. This is the main web interface for LOD Atlas. On the left side, there is a list of facets, available facets, and the right-hand side is divided into a series of sections. On the top, we have the search section where we can make a keyword or URI search on datasets name, title, or description, or the classes, properties, or vocabularies used in the datasets. And the search executed on classes and properties is actually executed on either on the URIs or ontology labels of the datasets. And following the search section, we have an optional filter section where you can apply various filters to narrow down your search results. And below the filter section, we have the list of datasets resulting from our search, selected facets, and applied filters. Actually, this result set is a basis for selection of data sets of interest. Below this list, we have another list which is initially empty. And we call this a dataset cart in analogy with a shopping cart where you can save the datasets that you are interested in. This is a simple overview of the interface of the LOD Atlas. Now I'd like to go through a scenario to discover the features in more detail. Sorry. So let's say that I'm a user interested in the data sets related to genes. I make a keyword search with gene on the... it's a bit difficult to see the fields, but you can visit the website and see it in more detail. I execute a keyword search on name, title, and description of the data sets. And I am also interested in the data sets which use the vocabulary bio to RDF. So I put an additional field to make search among the vocabularies used in the data sets as a disjunctive query. And from the facets, I select data hub to only view the results coming, the data sets published through data hub. And also I select data sets which are tagged with life sciences. And as a result, I have 32 data sets. At this point, I have an option to check analytics on the data sets. This is the analytics view. It enables users to have an insight about the characteristics of the data sets in my result set. It comprises of 6 charts. The first 4 displays the information on the number of triple counts of the data sets, total number of links of the data sets, the outgoing links and incoming links of the data sets. And the final 2 timelines display the creation and last modification date of the data sets. And in this view, all charts are synchronized. When you hover a data set in one of the charts, it's highlighted in all of the charts so that you can have an idea about the values in all charts. So going back to my main interface, I add 2 filters. In the first filter, we can see the number of triples in horizontal axis, and on vertical axis we see the number of outgoing links. And here I can just filter the data sets which have triples, triple counts more than 70,000. And I apply a second filter for which displays the last modification date of the data sets to select the recently updated data sets. So from this search, I obtained 23 data sets. Now I can put the ones that I'm interested in to my data set cart. And here is the data sets that I selected. I select all of them. And at this point, I have an option to export the void descriptions to a file, or I can further explore the data sets and their relationships through a series of interactive charts. The first one displays the triple counts of the data sets. The second one displays, it's an adjacency matrix to show the links between the data sets, and next to it there's another radial network that displays the same information but in a more intuitive way maybe. And the final 2 timelines display the creation and last modification date of the data sets. We have some other charts, but they are not displayed here. Besides these collective views, we also have views to get information about individual data sets. This is the dataset details view, and it's organized in 4 tabs. The first tab displays the metadata downloaded from the catalog. In the second tab, we have RDF quotients tab. This displays the summary generated using RDF quotients framework. Next to it, we have the list of vocabularies used in the data sets, and we have direct links to the vocabularies and LOD sites when it's available. And the final tab is analytics tab for individual data sets together with their linking data sets. So this is a basic search scenario in LOD Atlas. Thank you. I already have one here, but thank you. But we can use LOD Atlas for other scenarios, like monitoring data sets that are recently added to the catalog or that are recently modified. For example, in this view, analytics view for DBpedia, we can easily identify the data sets which are recently added to the catalog and feature links to DBpedia. And we can do the same for the recently updated data sets. Another scenario can be spotting noteworthy events in a selection of data sets. In this analytics view, when we sort the charts depending on the creation date of the data sets, we observe a time span that the number of links of data sets is substantially large. And actually, when we hover the data sets, we see that this is the time span corresponding to the addition of RKB data sets to the catalog. And a final scenario can be comparing and contrasting the contents of the data sets. We can compare the summaries of the data sets, the vocabularies used in the data sets, or we can compare the analytics on the data sets. The use cases can be multiplied when the users start using the interface, and they can also propose some new scenarios, actually. This is all what I want to tell about LOD Atlas and features. Now I would like to tell you about technical aspects of the program. Sorry. LOD Atlas comprises of mainly two modules, LOD Atlas Data Manager module and LOD Atlas Web Server module. The data manager basically downloads the catalog metadata and then downloads the resource dumps and processes them to extract extra information. And the LOD Atlas Web Server provides a web client where users can query and visualize the content that is generated by data manager. And we also provide a REST API for the users to programmatically access the content that we provide. And this figure illustrates the data processing workflow. Very briefly, what we do is download the catalog metadata and identify the RDF dumps and download them. We first process them with LoadStats to extract vocabulary, properties, and classes used in the data sets. And then we process them with RDF quotients framework to extract summaries. And finally, we index them as Elasticsearch indexes. As I said, we made the REST API public so that interested users can get the data, the content that we provide. And here are some links that you might be interested. The source code is open and licensed with GPL version 3 and is hosted on INRIA's GitLab repository. And we also provide a Docker bundle so that you can have an instance of LOD Atlas on local and process the data sets, the data catalogs that you are interested in. And here are some statistics. Up to now, we have processed Data Hub, DataGo, and European Data Portal. The first two are completely processed, but European Data Portal is still being processed. As you can see, the RDF quotients are not available for all data sets. To have the RDF quotients, this workflow must finish successfully. However, for some data sets, the resource dumps are not available, especially for Data Hub. Actually, when we processed in April, we had a better coverage, but since then, many resource files are no more available, so the coverage rate has fallen. And for the cases when we have dump files, for some files we have syntax errors that prevents them from being processed. And finally, It's especially for the RDF quotients framework that it requires significant resources when the size of the files grows large. So we have to limit the files that we can process. And finally, we have started working on LOD Atlas in 2015. And by that time, we initially considered working on with LOD Cloud datasets, and which was hosted on Data Hub. And it was a main gate for the linked data datasets. However, it's no longer the case now. So we considered adding an interface to submit new datasets so that we can have up-to-date information and process the datasets. And after announcing in public LOD data list, actually it was proposed that void descriptions, to submit void descriptions instead of providing such an interface, which is actually very convenient. So we are considering to do that. And when we introduced this interface, actually LOD Cloud hadn't yet announced that they were going to provide a similar interface. But recently they have announced this, and now we are considering, we are thinking that it could be nice to mutualize this effort so that users don't need to make a double effort to submit data sets. So this is all I want to tell you about LOD Atlas. Thank you for your attention, and I'll be happy to answer your questions, if any.
Thank you very much. Oh, there's lots of questions. Let's start. I do it in order from front.
Thank you. That looks a great tool. Have you done any user evaluation to see whether it actually helps people find data sets of use?
Actually, not really.
Okay, hello. It's excellent. I like it. My question is, you mentioned that you are able to somehow find out the connections between the data sets. Is it done on the level of the summaries only, or are you going also to find interconnections in terms of particular data?
Actually, we get them from the catalog information. In Data Hub, the links of data sets are also provided with the catalog information, but if it's not provided, actually we cannot serve it.
Okay, so you basically do it on the summary level. So you make the summaries and find the links on the summaries, or
no? In
not
the
not
summaries,
even
we get a quotient graph, which extracts the property usage of instances of classes. The summaries is different. We don't get links from the summaries, actually. It just shows the links inside the data set, we can say.
Okay, thanks.
And another question?
Hello, thanks very much. It looks like a fantastic resource. I completely agree you should be doing more user research. But, as a potential user, I think I'm going to try it out right away. So that's my comment. And
we'll be happy to hear your comments, actually, and feedback.
So my questions, I have a couple of questions. One is about dead links. So in the past, I've been using the Link Open Data Cloud to find data sets. A lot of these data sets were not existing anymore, or maybe the links they provided were dead.
Yes.
So I was wondering how you treat those links. And the second question is whether you're fully compatible with the latest version of the LOD Cloud.
We are not yet compatible with the latest version, but actually it's very simple to do that. But before coming to here, we didn't really have time to implement an interface for LOD Cloud and process it, because it takes time to process the data sets. But it is something that we are going to do in the first place, actually. What was your other question? We just don't process them, but we give information that that link is no more available.
So thank you very much. Thanks to the speaker again.
Thank you.
That concludes our session on time to the second. I wish you a good afternoon and enjoy the next sessions. Thank you. Right now we have a coffee break.
Somebody's power
Oh, that's probably Ricardo.